So without further ado, it is always great to introduce a friend as a speaker. And Dan Creighton, in addition to everything I'm about to tell you, is one of our newer board members. He's also our treasurer, which is probably the most thankless job we have, but he does it with grace and with great acumen, and we really appreciate that. Dan earned his bachelor's and his master's in geology at the University of New York in Buffalo. His master's thesis, not too very far away to the west, a study of the Menin Buttes near Rexburg. This is part of a NASA program using field geology on the Snake River Plain and comparing it to geology on Mars. The projects in support for Mars exploration plans. While mapping the buttes, Dan camped there in 1980 and managed to sneak over the mountains and explore eastern Idaho and western Wyoming. And that was the seed that got him to move out here. Unfortunately, he had to work for 36 years first as a petroleum geologist and geophysicist all over the world, the United States, China, Colombia, Angola, Mozambique, Cote d'Ivoire. His last 10 years were unconventional oil and gas projects in Texas and Oklahoma. Finally, 4 years ago, Dan moved to Jackson with Cynthia Blankenship, his wife, who's also given some excellent talks for us and is on the board, and his 3 children. He continues to work part-time as an advisor to Burgundy Exploration, doing oil and gas work in Alaska. So without further ado, Dan, it's all yours.
Thanks a lot, Mike. I hope everybody can hear me well. And I'd like to state initially that my original plan was to cover both earthquakes and groundwater issues, but that was going to take too much time. So tonight we're just going to cover earthquakes and mostly how it relates to hydraulic fracturing, but wastewater disposal is another issue that's involved. So without further ado, let's move to an outline of what we'll cover. We'll just do a brief overview of U.S. energy use. Then we'll talk about oil and gas related earthquakes, how they occur. Then we'll cover, just for background for folks that aren't familiar with the oil and gas business, we'll cover some basics about conventional and unconventional reservoirs. Then we'll talk about the different types of wastewater injection that the oil and gas business uses. Then we'll have some examples of earthquakes directly related to wastewater disposal, cover history of fracking, and then I'll cover unconventional well design, so you can see how we design wells to make sure that we don't contaminate drinking water. And then we'll cover some examples specifically related to earthquakes from fracking. And then I've got some conclusions. So let's take a look at US energy consumption. This is a chart showing relative amounts of energy used from 1949 to 2019. The y-axis here is quadrillion BTUs. That's a hard thing for me to get my head around, but anyway, it's a lot of energy, I believe. So we have different types of energy use, and you'll notice here around 2006, coal began to start dropping off, and we started to use much more gas. That was the start of the US shale fracking revolution, and that just really changed our use of natural gas versus coal for electrical energy generation. Let's move over to the next slide here, and this is U.S. energy imports. It has the same y-axis, quadrillion BTUs, covers the same time frame. And again, you can see that our energy import was increasing until about 2006, and that's when fracking for both gas and oil started, and our energy use dropped off. And in 2019, we actually became net exporters of energy. Now let's step on to oil and gas related earthquakes. So oil and gas related earthquakes typically are caused by reactivation of existing faults in the subsurface. This slide shows in schematic form an injection well injecting wastewater into the subsurface. And then if there's a connection from that formation that the water is injected into to a fault, it can increase pore pressure and cause that fault to slip. Pressure increases can be done either via wastewater injection, which this really is showing, and then also from hydraulically fracturing a well. Now on the right-hand side, another way of causing earthquakes is to have multiple wells going into a large reservoir, here shown by the ellipse. And if you remove enough volume out of that rock, you can unload the crust, and that can cause a fault to move. Or if you do an injection, you get enough volume into it and cause fracturing, and can also get that fault to move. So also we need to know the earthquake scale and its effects. So most induced earthquakes, typically by oil and gas activity, are less than 3.5. So they're almost imperceptible. And the lion's share of them are below 3, only felt by seismometers. We do, however, have induced earthquakes that have been attributed to oil and gas operations up into the upper 5 magnitudes on the Richter scale. And that's where we get some surface damage. Homes have brick fascia come off their walls, things like that. Now let's cover conventional and unconventional reservoir basics. For those attendees that are not as familiar with oil and gas operations, I want to give you this background view. So this shows different types of hydrocarbons. Conventional oil and gas has historically been the bulk of the hydrocarbons produced in the US until just recently. A conventional reservoir usually has good porosity and permeability so that fluids can move easily within the rock. Generally, a conventional reservoir is geometrically trapped beneath an overlying seal. In this case, we've got a shale on the left-hand side of this diagram, a shale that seals it. We have a fold, and this would be a 3-dimensional closure where the gas and oil has accumulated. This well was vertically drilled, and it went through gas on top of oil and oil on top of water. As we produce hydrocarbons, if the system is a closed system, does not have a very large water aquifer, pressure will reduce as we remove the hydrocarbons. If the aquifer below the oil is very large, as you produce the oil and gas, water will move up into that reservoir area and pressure will be maintained. This is important because that depends on how you dispose of the water produced from that conventional production. An unconventional reservoir is typically an organic rich shale. This is shown by the organic rich. On the right-hand side, we have a horizontal well into it, and it's got some hatchers just distinguishing it from the other layers. Typically, an unconventional well has to be drilled horizontally and then fracked to get hydrocarbons to come out. There's one third type of well, and I'm calling that pseudo-conventional. And that's where it's a formation that has it's a conventional reservoir, but it's very poor quality. It has low porosity and permeability. And in the past, they've been drilled with vertical wells, and they produce poorly. By drilling horizontally into a poor reservoir and then fracking along it, you can increase the amount of fluid you get out of it. And that's a big factor, especially in Oklahoma. The Mississippian lime in Oklahoma is one of these major pseudo-conventional targets. So we talked about conventional oil field production, and I need to show this real quick. This is a graph of typical production profile from an conventional oil field. We usually start out with mostly oil production. It peaks, and then over time, water production will increase. And then eventually the oil reduces, and mostly we're producing water out of these old fields rather than oil. And at a point where the cost of getting rid of the water is more than the value of the oil we're producing, that's when you close in the old fields. So now let's talk about the different types of wastewater injection. So here we have a schematic of a field where there's not a strong water drive. So oil is being produced, that's going off to market, and the excess water that's being produced is going back into an injection well and being injected back into that same formation. And there are two reasons for doing that. One is to maintain the pressure in the reservoir, and the other is to also recycle the water back and forth, getting lower and lower concentrations of oil over time. So it increases the amount of production we get out of the formation by re-injecting that wastewater back into the formation. Now, I might indicate, though, that in general, we haven't changed the pressure in the producing formation. And so this type of wastewater injection rarely causes earthquakes. Another type of wastewater disposal or injection is when the pressure in the formation is staying the same while you produce your oil. That's where you have that big aquifer that's able to relax and go into the formation. The water that's produced is put into a wastewater disposal well and usually disposed of deeper than the target that you're producing from. So now let's talk about earthquakes that are known to be directly related to wastewater disposal. Our first example is the Rocky Mountain Arsenal wastewater injection program. In the upper left is a map showing the position of the injection well, Denver International Airport, and then the city, Denver City Center. This is a cross section showing the Rocky Mountain thrust front, and then going down into the basin out in front of it, into the foreland. And then here's Denver, and there's the Rocky Mountain Arsenal well, injection well. It's about 20 miles east of the Rocky Mountain thrust front. You might think that that's quite a distance, but for such a big fault system, most of this, especially the basement rock, is faulted and fractured. The disposal well, the disposal well was drilled to a depth of 12,045 feet with its bottom in fractured Precambrian basement, as shown right here. Drilling data indicated that the Precambrian was permeable due mainly to a natural fracture system that was in place. Let's go to the next slide. Here is a Strat section showing what the well penetrated. On the left, it highlighted zones. So the injection is where the red bar shows you, and it's directly into Precambrian basement. And this is unusual. Most wastewater disposal wells are up into sedimentary rocks. So an important thing here is that prior to waste disposal here in the Denver area, there had only been one fault that was ever felt, and that was back in 1882. So now I want to show you two charts. One is the average gallons of waste injected per month in the Arsenal disposal well. The first month was 4 million gallons, and then they went up to 6 million and kept that steady for a while. There was a hiatus, and then they started injecting again. This was with gravity flow, and then they used higher pressure to inject. They went back up to 6 million gallons a month. The maximum pressures that were recorded during this injection were 550 pounds in the first stage of injection. And then after letting it just flow by gravity, then they had increased their volume and they went to 1,050 pounds. So it was taking more pressure later on to get that same amount of water disposed of. So during the period from 1962 to 1965, having not had earthquakes in Denver, they had 710 recorded earthquakes. The magnitudes range from 0.7 to 4.7 magnitude on the Richter scale. Remember now, 4.7 magnitude is on the verge of a quake that can cause damage at the surface. Another important point is that most earthquakes that were recorded were within 5-mile radius of the injection well. That's pretty good evidence that the injection was causing the earthquakes. They stopped injecting in 1965 when the link to the earthquakes was fully recognized. However, induced earthquakes continued to happen for 20 years after the injection stopped. So now let's go to the central US. This is a map showing earthquake epicenters from the time period 1973 to 2019. The earthquake epicenters are colored differently by timing. So from 1973 to 2008, they're colored blue. These are all earthquakes over a 3 magnitude, by the way. And then the earthquakes from 2009 to 2019 are colored red. Notice that in 2009, there was a significant increase in the number of earthquakes, which peaked in around 2015. So I want to highlight first, Oklahoma has the lion's share of these earthquakes that began to happen, induced earthquakes. Primarily, I believe the Mississippi lime play, that pseudo-conventional production with lots of water, is in that north central part of Oklahoma. There are a couple of shale plays down in the south that also contributed earthquakes, but we'll mostly talk about that Mississippi lime play. Another area that contributed to this spike in earthquake activity was the Barnett Shale in North Texas. And that's shown by here. You can see though the earthquake activity is much less than in Oklahoma. So let's look closely at the Oklahoma wastewater injection related earthquakes. On the left so this is a strat column showing the injection zone, the Mississippi line, which is the primary producer that made all the water. And then that injection zone sits directly on Precambrian basement. Here's a map of showing earthquake densities prior to 2009. This is a scale showing, a color bar showing the scales of the earthquake epicenters. And you can see these are all gray. So they're down there really below 1. Then, starting in 2009 through 2018, look at the huge number of earthquakes that Oklahoma suffered. In this case, we have 4 earthquakes that are 5 and above. And some of these caused damages, and now we've got lawsuits and things trying to resolve who's going to pay for the damages that people suffered. So prior to 2009, there was significant oil and gas wastewater injection into the Arbuckle for over 40 years. That was mostly from the old conventional reservoirs, but the wastewater volumes were less. Once we started actively drilling horizontal wells and fracking, wastewater injection volumes seriously increased. The Arbuckle was a good injection zone because it accepted large volumes of water and was much deeper than the freshwater aquifers, but it appears that we've overwhelmed it. There's now documentation that the Arbuckle has been pressuring up over time and that fluids may be migrating via fractures into the faulted and fractured basement rocks, creating all these earthquakes. As we discussed earlier, increasing pore pressure can reactivate dormant faults, pretty similar to what we saw with the Rocky Mountain Arsenal case. Now let's take a look at the North Texas situation. There were no felt earthquakes in North Texas for 160 years prior to 2008. Here is the situation. The injection zone is the Ellenberger, which is mostly a dolomite package, and it sits directly on Precambrian basement. So it's very similar to the Oklahoma case. The Barnett Shale is the shale zone that was produced, that became a drilling target for horizontal wells. And we saw an increase in earthquake activity after this drilling activity started. Here's a map of the Fort Worth Basin. The map is colored by injection volumes. The bluish color is low volumes, less than 800 cubic meters of injection by area. The red map color over here, they have injection levels of as high as 46 million cubic meters of volume. The blue dots on this map indicate injection wells. So these injection wells were disposing of huge volumes of water. The red dots represent induced earthquake epicenters. And you'll notice that there's been an increase in earthquakes, and they do seem somewhat linearly organized, so maybe along faults. So as in Oklahoma, the Ellenberger appears to be pressuring up and is now causing induced earthquakes. We are seeing similarities between Rocky Mountain Arsenal, the Oklahoma earthquakes, and the North Texas. Injecting close to the basement rocks is a condition where we see more earthquakes being caused. Now let's go into a brief description of the history of fracking. In the 1860s, hydraulic fracturing was first started by using liquid or solid nitroglycerin. Then in 1862, Edward Roberts designed elongated shells and filled them with gunpowder, and he was able to get more precise positioning of the explosions to fracture the rocks. Most of this frac activity was in the Northeast in fairly shallow hard rock formations. Then in 1947, Floyd Ferris designed a hydraulic fracture process while working in Hugoton Field in Kansas. In 1949, Halliburton and Floyd's employer, Staniland, improved the process that he designed and then patented it. And that had been the process that's been used for years up till now. One last person to mention is George Mitchell. In the 1980s and 1990s, he and his team combined fracking with horizontal drilling in the Barnett Shale. That was the North Texas activity. However, it took until 2006 for the technology of horizontal drilling and fracking to be improved enough to be used on a grand scale. So Mitchell's legacy is to have designed or conceived the idea of hydraulic fracturing in horizontal wells. Now let's cover unconventional well design. Here's a schematic of a well bore, and it's shown going down into a shale that is a hydrocarbon target. When we start up drilling a well, the first thing that happens is you set a conductor casing, here shown in yellow. That casing is either driven or drilled and then set. It's not usually cemented, but it helps guide the drill pipe for drilling the shallow section of the hole. So while we're drilling that shallow section of the hole, we use either air or water to keep from contaminating the freshwater aquifers. Once we've drilled that surface casing or that surface section, we set steel casing, run cemented in place. So we run cement down through the pipe and then up the outside between the rock and the casing. And then before we can drill on with the well, we have to pressure test that casing shoe for integrity to make sure that the freshwater aquifers are protected. Next, we start what in this case would be called the intermediate casing. So we drill this to protect both formations in this section from communicating with each other and also communicating with the target interval. As with the surface casing, we run the pipe, cement it. You have to pressure test that shoe before you drill on. And then finally, you drill the production part of the hole. And what we call production liner is run. So the steel pipe is run to the end of the horizontal well, cemented in place, and pressure tested again. So in the end, what we have three steel casings that are protecting the aquifers, and we have three cement layers closing off those casing zones from the rock that they're embedded in. So after the well is drilled and cased, next thing that we have to do is move in the frac equipment. So you'll notice there's quite a bit of equipment here on this very small location. It takes a lot of logistics to get that equipment and all the frac materials in place. Notice there are a lot of tanks here. That's probably the fresh water that they're holding. So after getting all that equipment in place, now we're going to do a frac job. So here's a schematic of the well. It shows 6 stages of frac. In many cases, we have as many as 30 to 35 fracture stages in a single well. We call the toe of the well the end of the horizontal leg, and then we call the heel the part where we start to go horizontal. So this would be the heel right in here. Now the first stage the first thing we do for a frac stage is lower a perforating gun down the hole, put it in place for the first stage, wherever that was designed, and we shoot holes in the production liner. If you look up here in the upper right, so this is the well casing, and these black dots represent holes that were shot in the casing using shaped charges. Next, we start pumping the frac. So first we start with water, which initiates the fractures. And then as the job moves on, we start to introduce proppant, a mixture of water and proppant. So the proppant, often it's just sand. It goes out through the holes and into the fractures, and it's designed to keep the fractures open once pressure is reduced, to keep the fractures from closing again. After completing the frac stage, a plug is run down the wellbore and set near where the fracture treatment was. That separates that fracture system from the rest of the well. Next, we do the same thing for stage number 2. We run the perforation gun down the hole, pump the frac job, and then set a plug. And we continue to do that until we've completed all the stages that we've designed for the well. So hopefully that gives you an idea of the operation of fracking a well. Now, another question that we have is, what is the typical area and volume that's impacted by a fracked well? The well is usually, well, I'm just going to use average numbers here. So a shale well is often about 1 mile long. The fractures that we induce are about 200 feet tall. And the fracture length from the wellbore, this black dot is the wellbore, as you move outward. So we have about we usually design them to try to make 1,000 feet of fracture length, and that's 1,000 feet in both directions. So when you compute the volume of rock that entails, it's 50,000 acre feet. The subsurface area is 250 acres that's impacted by the well. And then you take the 200 feet and it's 50,000 acre feet. So acre feet, that's a hard thing to get your mind around if you're not used to using that type of measurement. So I'm giving you an example of the Louisiana Superdome. Superdome is 273 feet high, and it covers an area of 13 acres. So that volume that the Superdome entails is 3,550 acre feet. So 50,000 acre feet for the average frac well is equal to about 20 Louisiana Superdomes. Now I know that sounds big, but in the grand scheme of things, when you compare fracking wells versus wastewater injection, this is actually a small volume. So how likely is fracking to induce an earthquake? So induced earthquakes are usually caused by reactivating an old fault. That means a frac well, because of the limited volume that it influences, it needs to be pretty close to an existing fault to cause an earthquake. Also, when we are planning our wells, usually we try to avoid faults, and that's really because if you start your frac stage and it leaks and it goes into a fault, you lose pump pressure, and basically that frac stage is a failure. So overall, in most cases, we try to avoid faults with our frac wells. So let's cover a couple of cases where we actually know that earthquakes have been directly the cause of fracking wells. First example is in Echo Field in the Horn River Basin in Canada. The operator had 3D seismic and mapped numerous faults in the area where they were drilling. Part of the wellbore is shown, of a wellbore is shown here, and these 4 discs represent 4 different frac stages for that particular well. The colored dots here are microseismic measurements of fault activity. The dots are sized for magnitude, although I don't know what the magnitude, I didn't have a scale for these different sizes, but also they're colored based on which frac stage they were from. And also this paper did not tell us which stage they were from, but it looks like you've got at least 3 different colors here. So at least 3 of these stages contributed to microseisms down a fault plane. In this case, only 1 induced earthquake was actually felt at the surface, and there were no injuries or property damage related to the activity. The one thing that we know, so there has not been any prior wastewater injection, so it's pretty obvious that these induced earthquakes were related to the fracking. Now let's take a look at a induced earthquake example in Harrison County, Ohio. This is far eastern, east central Ohio. These are 2 cross sections, one east-west and one north-south. These wells were drilled from a pad and went into the target zone. In this case, the target zone is the Utica Shale. These are the same well bores, just from a different orientation. Now, below the target zone, notice that we have a lot of colored circles. This dotted line represents Precambrian basement. So from the base of the target zone to here is Paleozoic rock. And then this is Precambrian basement. Notice that these are really out of zone. So these are microseismic events that were recorded and shown to be outside of what the operator was trying to frac. It's really interesting that they got all the way down into Precambrian basement. So there appears to be a pre-existing network of faults and fractures that allowed fluids to communicate downward all the way down into the Precambrian basement. The one thing that was noticed here, though, is the Paleozoic rocks had lower magnitudes. Generally, they were less than 1 magnitude on the Richter scale. But in the Precambrian basement, the induced earthquakes had a lot larger magnitude, usually in the range of 2 with a maximum of 2.5. So having these different sets of induced earthquakes mean that there's got to be some sort of a hydrologic or hydraulic connection between the Paleozoic and the Precambrian. Again, as in the Canadian example, there has been no wastewater injection here, so we know that these induced earthquakes were directly related to the fracking. So let's talk about what we've learned. So do oil and gas operations generate induced earthquakes? Yes. Is wastewater injection responsible for most induced earthquakes? Yes. Does fracking cause induced earthquakes? Yes, and more than previously thought. The biggest problem, and why we did not know that fracking caused earthquakes as much as it may, it's because a lot of frac operations were where we were making significant wastewater injection. So we already had underlying induced earthquakes happening, and it was tough to break them out from the frac jobs to the wastewater injection. So one of the things that's key here is proper use of monitoring technology can provide early warnings if we are having induced earthquakes, especially during a frac job. If you start seeing microseisms above what you expect in the target zone, you can shut down the operation before you create anything that could be dangerous. Same thing with wastewater injection, although there's usually a long delay when you start wastewater injection before you start seeing the earthquakes, except in the Rocky Mountain Arsenal case. Anyway, so the state regulatory agencies are really on top of this after we had that big spike in earthquakes in the central US. They need to continue to develop regulations to help manage and mitigate any induced earthquakes that we might generate. And with that, thanks for your attention. Sorry. And I'm open for questions. Let's see, do I have to mute?
No, you don't have to mute yourself. In fact, you should stay unmuted. I'll go ahead and read some questions to you here, Dan.
Okay.
So, and if anybody has more questions, use the chat function and send them along to me, John Heberger, if you would, please. Just pick my name out of the chat options. So, couple of, well, a bunch of questions, I guess. How deep were the earthquakes at Rocky Mountain Flats? And if, as it seemed, they were mostly in basement, how come?
So the earthquakes, so the well was drilled 12,045 feet from the surface. So that's not, on the cross section it showed subsea, so that's a little confusing, but they were 12,000 feet below the surface. And the general consensus for the reasoning of the almost immediate effect of induced earthquakes was because the injection was directly into crystalline fractured basement. And it's been noted in many studies, both in Oklahoma, North Texas, and elsewhere, the closer wastewater injection is to crystalline basement, the higher the probability of induced earthquakes and higher magnitude earthquakes.
Okay, related to that, why more and bigger earthquakes in basement rock as opposed to sedimentary rock?
Well, that's a good question. Presumably, the faults and the overburden are less stressed, and the fractures in the basement are higher stress levels. I know that's not a very good answer. I could try to find more information about that.
Okay, another question is related to the drilling of the wells. How do you get steel to bend 90 degrees in a heel like you showed?
That's a good question. It's you just basically on the bottom of the pipe, as you're running in the hole, there's a rounded nose that's put on it that's called the shoe. And that just allows the pipe to follow the hole that was drilled. You have the same problem with drilling pipe too. The drill pipe has to bend, although the drilling pipe is less in diameter than the casing. So casing, sometimes we do have trouble getting the casing down the hole if there are washouts and rugosity to the borehole. But generally the pipe bends, as you put enough pressure on it.
Okay, how far do we know that earthquakes can occur from injection wells? How far away do we have that documented?
Boy, I don't know that we have specific documentation of that sort of thing. The problem is in the areas where we've been doing this wastewater injection where the earthquakes started, we've been injecting there for 40 years. And it wasn't until we really ramped up our activity and had a lot of frac water and a lot of associated water that needed to be disposed of. So we, because we bumped up our production so much, we also in probably a magnitude of 100 increased the amount of water we were injecting.
Okay.
So I can't really give a specific on how far, but so the Ellenberger itself is known to transmit long distances.
Fluid, you mean?
Yes. Yes.
Yeah. The Oklahoma series of earthquakes, they declined or nearly stopped in 2016. How come?
That's because in 2014 and 15, people were getting quite agitated by having their houses shake. And the Oklahoma Commerce Commission began regulating wastewater injection as well as fracking. Basically, they started monitoring. They reduced the volumes that were being injected significantly and shut down a number of wells. And that caused that significant reduction in earthquake activity. And I might add, so I had a slide that showed the whole central US. The spike in earthquakes was really dominated by Oklahoma.
Okay. Question about fracking, and that is what constitutes a typical hydraulic fracturing fluid? What are the chemicals that are in it and may be of concern, and why do companies hold those formulas so tightly? So why do they not publish what's in those?
The fluids that they use, so 99% of the liquid in a frac is water. And then there's about 1% is surfactants, biocides. So you have to treat the water to make sure that we don't put bacteria into the reservoir and start having bacteria eat the hydrocarbons. There are other chemicals that are used just to facilitate having the water be correct for easily pumping down the well. I don't have a full list. I wasn't prepared to cover that, but in the old days, well, at least in the beginning, the service companies protected their recipe for frac fluids. They had a lot of proprietary things they were putting in there. There are very few really bad chemicals in frac water. It's mostly surfactants and other chemicals that you even use in your house for cleaning.
Okay. Has there ever been a producing field shut down as a result of earthquake activity? If hydraulic or wastewater injection?
I haven't looked up to see when they shut in those injection wells in Oklahoma. The Mississippi lime trend was where most of that wastewater was coming from, and I would have to presume that they had to shut in wells, if they couldn't inject the same volumes that they were trying to. So yes, I would say so. Maybe not. The problem is the Mississippi lime is not a field; it's thousands of wells. And a lot of them are different classifications by field, but the Mississippi lime in general, yes, they would have shut down many of the wells that were, if they had an injection well that was told to be closed down, they would, most of the water that was going to it from certain operators would be eliminated.
Okay, comparing a hydraulically fractured well versus the water that goes into an injection well, how much difference do you think there is roughly in the volume of fluids? In
a typical shale well, when you frack it, you only recover about 50% of the water. The shale is kind of imbibes the other half of it. So the wastewater from a frac well in a shale play is generally 50%. The Barnett Shale is a little bit of a, in North Texas is an anomaly. It's got some water sources adjacent or nearby that seem to get into those wells. But for the most part, 50% of the frac water comes back out. And that's then disposed of through wastewater disposal injection.
What's the makeup of the wastewater that is injected, and you know, is it really fluid? Is it fairly viscous?
No, it's pretty much just water. What you'll see is you'll have your frac fluid come back, and that is low salinity. Usually we're using fresh water for the fracs. And then over time, as you watch we usually catch water samples of the water that's being returned, and pretty soon you'll start getting formation water, and that has higher salinity. So you'll see that salinity increase as you produce the well over time.
Okay. Question, this gets a little bit beyond what you had the scope to cover here, but what is causing the contamination of private wells in the Pavilion, Wyoming area?
Okay, that's getting ahead. I hope to have a presentation about that soon.
We hope you do too. Go ahead though.
Yeah, I'll
give a preview.
Okay. In Pavilion, there are freshwater aquifers down to almost, I think, 1,500 feet, if I remember correctly. And the depth that that surface casing must be set is like at 800 feet. And so depending on where you live, you know, you may have to drill deeper to get your fresh water, your water well to work. In some cases, you might not have a shallower aquifer. And what's happened is Pavilion Field has these surface casings set in the middle of the freshwater system. And so the old wells, you know, if you've produced and have any kind of a leakage, the older wells were not as well designed as contemporary ones for protecting aquifers. And in this case, the surface casing is too shallow, and gases from the production systems has gotten into the aquifer system. Now, there also were gas reservoirs within that aquifer system. So naturally, gas had moved up into that shallow aquifer system. So it's both leakage from the field and natural processes that have caused gas to be in water wells that you see there.
Okay, coming back, sort of related question to the drilling itself again, or actually the running a casing. The question is, how do you engineer a bend in the steel casing? You know, could you flesh that answer out a little bit? Yeah,
so that bend, you know, when you look at a diagram on a PowerPoint slide, it looks pretty sharp, but the casing is flexible enough to make the turn at the rate of bend that we drill the wells. So you drill, we have both short radius and long radius wells. Short radius is a little bit more challenging. Sometimes it's hard to get your casing down because you're having to bend it much more. But typically we design the curve of the well to facilitate getting the pipe down and having it flex enough to be able to push down to the bottom.
Okay, question about the injection fluids. Do you have to use fresh water?
That's a really good question. And no, we don't. And this is a pet peeve of mine. So in a lot of places where we have horizontal drilling and fracking, we have to source the water. And often there are brackish water reservoirs below the surface casing. And you can actually drill and complete a brackish water source well. But the problem is when we lease land, the rancher or whoever leased the land to us, a lot of times these lessees have large acreage positions, and part of what they do is they make money from the oil and gas operators. So they require you to buy fresh water from them, and they're using the water that they irrigate their crops with, but they want to sell it to you as well because they can make a profit on it.
Okay, in a fracking job in a horizontal well, how far apart are the frac stages typically, and how are they separated?
Okay, they vary quite a bit. Some of the wells that my company drilled, we separated them they were 150 to 200 feet apart. Some other operators, they'll try to lower their costs and have less stages, frac stages, and they might make them 500 feet apart. And it really depends on the specific target that you're after, the type of rock it is, how best it works. The way you separate each stage, so you have a production liner that you ran to the bottom of the hole and you cemented it, and each frac stage is separated by a plug in the casing that separates each stage from the next one. There are other types of mechanisms we can use. Sometimes operators complete in an open hole, and they use packers to separate the stages while they're actually conducting the fracking. Those are the open hole packers.
Okay. Another question about setting the casing, basically, or drilling and setting the casing. What is the radius of a long turn is the question.
It varies, of course. You have short radius and long radius. We typically drilled a medium radius, and it took about 1,500 feet laterally to go from vertical to horizontal.
And if you did a real tight, how tight can you go with that?
I think they get as tight as 500 feet laterally.
From vertical to horizontal?
Yes.
This is maybe more about the economics. If you can't inject the wastewater because of regulations, what are other options for its disposal, and when does that begin to make the drilling or production uneconomic?
Good question. In Oklahoma, the Mississippian lime has salinities in about 60,000 parts per million, or 60,000. So it's about twice the concentration of seawater. So there really isn't anything to do with that water except deep injection. So basically, I think if you're causing earthquakes, basically you just can't afford to produce that. And so I think you'll see a lot of Mississippian well producers being shut in and probably abandoned soon.
What kind of regulations, monitoring have state surveys instituted to try and stop what happened in Oklahoma?
Many states are now requiring that you, if you are setting up a frac operation, that you have to set out some seismometers in a good enough distance around your operation so that you can record microseismicity. And generally the frac seismicity itself is usually negative magnitudes. So it's pretty obvious, if you get up into positive magnitudes, you've influenced something that you weren't trying to. And so, in fact, Oklahoma just recently lowered the magnitude at which they will require you to stop operations and talk to them. So if you reach a magnitude of 2, you have to give them a call, and they have a technical review of what you're doing. And you're supposed to stop your operation for at least 6 hours until you've had words with them, and then they tell you whether you can go on or not. And they call this a traffic light system, so they have different levels of magnitude where you can talk to them, and you might have to just slow down and not pump as much or pump less. And then if it's getting up into the magnitudes of 3 or so, then they're going to shut you down.
What in Wyoming, what kind of regulations and or monitoring exist in this state?
I don't know. I have not researched that.
Okay. There's a question about you know, the frac stages, the plugs that are set. Basically, it's about do you drill out all of those plugs and connect all of the frac zones, or do you do it in separate zones? You know, how do you set up that production history?
Yes. So after you've completed your frac job, say you have 20 stages, the plugs that are set in between each stage are composite plugs. And so they're easily drilled up. So they go in with a drill bit with a workover rig and drill all the plugs out, and then start flowing the well back.
Okay, that's great. I appreciate it. I think unless somebody sends in something right away, I think we've covered all the questions that have been posed. So, you know, do you have any, does that raise any final comments in your mind that you'd like to share, you know, the series of questions?
Yeah, I'd like to emphasize that, you know, when Oklahoma first started seeing all the earthquakes, that was a surprise, and it was an unknown thing. We have a much better idea, you know, what are the factors that set us up for that kind of induced earthquake activity. And it's really now a matter of making sure that we develop our oil and gas resources responsibly, and make sure that we are aware of faults, where we're disposing of waste, what kind of volumes of waste we're disposing. We just need to be real smart about this. And you know, it's very costly to go through what Oklahoma has gone through. And a lot of operators are going to lose big investments by having to shut in their wells. And we just need to do it smarter up front.
Okay, there's a final message here. It's really not a question, it's more of a comment. And it's just a comment saying that your talk on groundwater contamination is something that would be very much people look forward to, and hope that you'll be able to put that talk together and present that.
Great. Okay, John. So we can talk about what time slot you want me to set that up for, because I know you're booked out. So, but I'm actually really interested in that topic. I've got a lot of data that I've already collected for it.
Yeah, great. Well, yeah, great, Dan. I think you can tell by the number of questions that this was enjoyed, appreciated, and a lot was learned by a lot of people here.
Okay, good. I hope, yeah, it'd be nice to get some feedback. I was unsure how much background to give, to keep people so they knew how operations worked and everything.
Well, people have my email address they should have, or they can send it just through the Geologist of Jackson Hole website to John Willott and I. And if people who are listening have some comments or thoughts, yes, please let us know about either tonight's talk, about the format, about anything.
Okay. One other thing I wanted to mention that I didn't, and that is, you asked me what else I could mention in that. Probably up until 2016, it was still widely thought that hydraulic fracturing a well or fracking a well did not have much of a probability of creating earthquakes. And again, that was probably because most of that activity was in Oklahoma, and you already had so much activity that when you did a frac job, it was lost in the noise from the wastewater injection earthquakes. So
great.
There are some professionals now who are studying hydraulically fractured wells induced earthquakes, and they're finding better ways to isolate those from the background earthquakes. And so it's there was one paper I read, but I was a little concerned about how they broke out some of the earthquakes. So something to be looked at in the future, I guess.
All right. Thank you very much, Dan. And I think we will look forward eventually to that subsequent talk about contamination of the groundwater and whatnot. Before everybody logs off, I'd like to just offer a couple of things. One is that next Tuesday, Teton Native Plants has a program on Zoom, also at 6 o'clock. And that was mentioned in our pre-meeting slideshow, or you can go to their website and find out some details about that, about the login details, et cetera. We encourage you to take a look at that. The next Geologist at Jackson Hole program will be what I think is a really interesting talk by Mike Adler about water in the solar system, and how that might, what the implications of that may be with respect to the search for life. And we believe now, just as a teaser, that even the planet, or dwarf planet, if you will, Pluto, probably has an ocean in its subsurface. So there's a lot of water out there, and so Mike will talk about that, and that's on Tuesday, January 5th. And if you go to our website, you can take a look at the 2021 program calendar, see in much more detail what we have scheduled for next year. And as Mike said at the beginning, we'd love to get back into the library and do this in person. And we're working on probably, Zoom has not worked too badly, so we probably will try some combination of both Zoom and live talks, for people that aren't in Jackson Hole when we give a talk. And I've been reminded that it'd be really great to thank our members for voting for the Geologists of Jackson Hole board members who were just re-elected. And you don't see most of really what happens that makes the Geologists of Jackson Hole work, but I can tell you that Geologists of Jackson Hole board members contribute an immense amount to making the programs work, to things happening at the schools. We have a scholarship effort now for one or more students from Jackson Hole. So there's just a lot of stuff that what our board does and what you contribute through your membership and our donations allows us to bring in great speakers and do other things education-wise in and around Jackson Hole. So many, many thanks. And we're now concluding tonight's program.